Hello interwebs, welcome to Let's Fix Computers, I guess. We're going to talk about fans again today. I did a video a while back where I discussed 3-pin fans versus 4-pin fans. So 3-pin being these guys and 4-pin PWM fans being, well, I would point to this one, but as you can see the connector on this fan is not entirely of this world right now. The advantages and disadvantages between them. And the too long didn't watch version of that is simply that 4-pin PWM fans use a 4th pin to feed in a speed control signal rather than using voltage to control the speed of the fan. And this gives you a much broader range of control over the speed of the fan. One thing I didn't get quite right in that video is that a lot of 3-pin fans can actually go down to very low speeds as well. And 3-pin fans are not inherently terrible, but you will always have more control with a 4-pin fan than you do with a 3-pin fan. So with that in mind, what I wanted to do in this video was demonstrate in a bit more detail exactly how that works. And in order to achieve that, I'm going to take apart 2 fans. So I've got a grotty 3-pin fan here that we're going to take apart. And I've got a grotty 4-pin fan that I'm going to take apart. Sorry, we're not sacrificing this Noctua to the fan gods today. And what I want to do is take these apart down to the little internal circuit board so we can track the signals inside the fan and see exactly how the signals that are being fed into the fan are converted into a rotating rotor. So before we get started, I'll just show you exactly what signals are going in and out of the fan. So first of all, we've got power going in. So I'm feeding in 12 volts, which is what standard computer fans run on. So there's 12 volts going into the fan on its power pin. So the first pin is ground, the second pin is 12 volts power. And at 12 volts, this fan is just running at maximum speed that it can achieve. And that's it, that's all there is to see. If this was a 3-pin fan, we would control this fan by turning down the voltage. Like so. If I turn down the voltage on my power supply here, let's go down to 5 volts. And as you can see, if we drop down, well, there's 4 volts, the fan decreases in speed. Oh, it's actually stalled. Oh, look at that. It looks like this fan needs at least 5 volts to start up. So there is our voltage control for this fan. So now we'll turn that back up to 12. So now we're back up to 12 volts and maximum speed. Now because this is a PWM fan, a 4-pin fan, we can manually control the speed using a PWM signal. So over here I've got a signal generator, and down here I've got a pocket oscilloscope that reads that signal. So what we'll do now is we'll feed in our PWM signal. As you can see, we've got 25 kilohertz at 50%. So there is our square wave PWM signal. And what that is doing is it's telling the fan to turn on and off 25,000 times a second. And half of the time it is off and half of the time it is on, hence 50% duty cycle. And that is how we're controlling the speed of this. Now, unfortunately, my signal generator is a bit pap and I can't change my duty cycle at the moment. However, as you can see, the fan is at low speed. And I'll just demonstrate that again. If I just disconnect the PWM signal, you can see the fan speeds up to full speed again. And once again, we reconnect that. And it slows down. So as you can see, by feeding in signals to this fan, we can tell it what to do. And the whole time here, we're still running at 12 volts. So that is what PWM fans are all about. Right, so let's get our poor donor fan. Still dusty. I'm going to leave the dust there just to trigger some people. And let's peel back the label and see what we can discover. This is going to be a destructive teardown, but what I want to try and do is I want to try not to damage. I don't want to damage the fan to the point where it doesn't function. Okay, there's a plug as well. Because I want to try and be able to power the fan up while it's open. That's the objective here. But I don't know how easy that's going to be. So with that plug removed, we can see the fan bearing down there. I think I need some tweezers in there. There we go. So there's the rotor removed. So the rotor just has a permanent magnet on the inside, and now we can see the coils on the fan. So these are 4 electromagnets, and these things will be turned on sequentially. So I'm not sure whether it does it alternating or one by one, but let's pretend for a moment. We'll actually test this, but we'll pretend that it does it one by one. So it'll go 1, 2, 3, 4, 1, 2, 3, 4. And by turning these on in turn, each time it turns on a coil, that will power up and repel the magnet in the rotor, and it'll push the rotor around. Which way around does it go? Yeah, it does spin that way. So by pushing on the poles of this magnet, it then pushes the rotor around. So you turn that on and it just goes and it starts pushing the rotor around. And that is how you drive one of these DC motors. There also exists AC motors. Now, AC motors are a completely different kettle of fish, and they're also quite complicated, and I don't want to try and explain how those work because I'm not 100% certain about it in my own mind. I know the theory of it, but I don't think I understand it enough to be able to explain it. But yeah, this is a DC motor, not an AC motor. Well, objective achieved. That saved me from getting the Dremel at any rate. Alright, so now we're super deep down, and you can see there's not a lot in here, which is why these things are mega cheap. So, what we'll do, let's just have a quick look at the circuit here. So we've got our negative rail there. That's going around to... Let's go around to there, to there. All the way around to the outside to there. Then we have a positive rail that comes in and goes through this resistor here. So that is 10 and 1, 0, so 100 ohm resistor. And that is going through to the first coil and then the control chip. This doesn't look like a chip, but it's actually the control chip. The reason why it's sticking up like this is it also has a built-in Hall effect sensor, which will be the speed sensor. Then that has got another pin that comes off and goes round there to here, which connects to that one. So that connects to the opposite coil to the first coil. And then it also goes through what I'm assuming is a fuse by the looks of things. And then that has a, what is that, 223? Yep, so 2, 2 and 3 zeros, so 22K resistor to the ground rail. And it goes through to this guy here, which is presumably, I reckon that's a transistor. So when that pulses on, this transistor will short this line down, and that actually couples with my suspicion earlier on that the computer is sending a signal to this wire. I think it's at 1 volt. So there's 1 volt going to this wire, and when this comes around, this guy shorts that to ground. So when there's a pulse here, that gets shorted to ground. So it takes this signal low for a second, and that then puts out the tacho signal. Then going back to the chip, this pin then goes round to that one, and then we've got one more pin that goes all the way. Then the last one goes round to ground again. So how are these coils wired up? This one has 2 connections, so it's a positive. Okay, so this is the positive pin for 2 of the coils, and then there's 2 negatives there and there. So it's driving the cathode. Okay, so unfortunately I've killed the fan, because if I try and put the rotor back on, the rotor will not spin freely. I mean, well, you can see it spins a bit, but it's not coasting. And when I actually power the fan up, there's not enough torque to spin the rotor. because it's not spinning freely. Again, as a comparison with the not broken fan, that just coasts. With just the slightest push, it coasts. So I've destroyed the bearing on this thing. Might have been to do with when I smashed it with a screwdriver. In any case, so that means I can't power it on and measure it while it's in action, which I really wanted to do. But we might still be able to demonstrate exactly how it works. So what I'll do now is I'll quickly just cut to a section where I'll explain how this chip here works, and we'll go over that. So here's the data sheet for a typical 3-pin fan controller chip. And if we have a look here, it is a dual coil brushless DC motor or fan application. So as I suspected, it is a two coils in pairs rather than individual ones. So it's pulsing them, alternating. And blah, 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 various things, operating temperatures and yada, yada. So let's scroll down through this. And as you can see, we've got exactly what we saw on the fan there. We've got the chip and two coils and some other bits and pieces. And now if we look down here, we've got the functional block diagram for this chip. And here we can see how it actually works. So there's a voltage regulator just to make sure that the chip has steady power. And the first section is the Hall plate, so the Hall effect, which is a magnet sensor. So what's going on here is when the Hall plate detects magnetic flux from the magnet in the rotor going around, it activates things. So we have a sensor here, and that is immediately put into an amplifier, which will be an op-amp or something like that. That then goes to a Schmitt trigger, and what this Schmitt trigger is doing is because we have a magnet going around, that is going to be putting out a very curvy wave. Now, we don't want a curvy wave going to our motor. We want strong on-off pulses of power going to our motor coils. So we've put that into a Schmitt trigger, which will convert a smooth sine wave into just simply on-off signals. It will have thresholds for on and off. So we take the incoming signal, we amplify it, then we run it through a Schmitt trigger to convert it into a digital signal. And then the output from that then goes to one of the two phases. So on the on cycle, we go down this route and we activate this transistor here. And that will short the cathode of the coil to ground. And thus, remember, the anodes were connected to the incoming supply on the 12-volt rail. So when this is shorted to ground, we then have a path for that voltage to go down to ground, and thus the coil is magnetized. So as the rotor goes around, switching these two outputs on and off in alternation, these guys are switching on and off in alternation. So when one goes on, the other is off, and vice versa. And thus we're getting pulses of power to each one in time with the rotor going around, because the rotor itself with its magnet is activating this Hall plate. So there's no logic in here whatsoever. It's literally just the Hall plate reacting to the magnet spinning around and pulsing power to each one. And that's it. Okay, right, now we've understood how this guy works, let's just see if we can trick it into thinking that it's actually working. So I'll put some power onto this thing. I'm just feeding in just 10 volts. And if we turn on my multimeter, so we've got 10 volts coming in at the input there. And then after we go through this, resistor, we drop to 4 volts. And we should find that one of the phases is on and the other is off. So phase 1 is on, phase 2 is off. So phase 2 goes to that guy there. So what we want to do is try and trick it into switching on phase 2 as if there's something going on. So I'm going to try and hold this all in one place very gingerly. And what I'm going to do is I'm going to pass a magnet in front of the chip to simulate the rotor going around. And what we should do is, if I get this right, we should see a kick of 4 volts. There we go. So now it's on phase 2. If I turn the magnet around, There you go. So by passing this magnet, we're tricking it into switching phases. Oh, I'm covering up the numbers there, but you can see it working. So now, as you can see, if I grab the rotor, actually, we may actually be able to reproduce this with the rotor. It's just impossible to hold this all together. That's the problem. No, that's not going to work. I can't hold it all together. So you get the idea. So there you can now see the 3-pin fan in action, and it's completely analog. It's a very basic circuit. And yeah, that's how they build these down to a price. So the only other difference that you'd find is if this was an RGB fan or an LED fan, there would be additional stuff on here to drive those LEDs. However, none of that is to do with the actual motor circuit. Right, 100% making this up as I go along. Let's do it. Okay, right. That looks more promising. Let's power this thing up and see if it works. And I can actually hold on to that, so we might actually get a better demonstration now. Okay, so health check. Once again, feeding in 10 volts. Power on. All right, it works. So that will be running at full speed, or nearly full speed, because we're at 10 volts, not 12. I'm undervolting slightly just because if I'm holding the fan blade or it's unable to run, I'm just underpowering it slightly just to try and help prevent it from burning out for whatever reason. I don't know if it'll do that. I'm just playing it safe, basically. So now if I fed in a PWM signal, that would cut down in speed. So let's test that just for posterity. Turn it off. There we go. Right. Now let's pulse that just so you can see it change speed again. We've already done this demonstration, but hey, it's probably one of the more interesting parts of this video. Right, okay, so there's full speed, and now when I connect the clock, you should see it's dropping speed again. There you go. So you could see that visual change in speed in the fan there. So obviously we don't have a tacho connected up to test, but once again I'll remove it. And you can see it spool up again. So there we go. So there's our PWM action going on. Power off. Right, so now we need to try and watch that happen. Is there a lot of... Oh yeah, no, that's just dust from cutting plastic. Cool, so let's have a look at the circuits on this thing now. Right, so once again, we've got a single-sided board on this one. It's a lot less obvious where things go. It looks like all the action is happening on the control circuit for this one. So let's get right in there and have a look at that. Okay, so that is an APX 9173 VV4DN. Cool, so starting at the bottom here, you can see we've got our 4 pins in. So we've got our ground, power, speed, and PWM. So the ground just goes onto this flood fill plane. So that's got a couple of resistors there going from 2 pins. And there's a capacitor on the IC for stability to the chip. And once again, this is a 2-phase jobby. You can see we've got 3 pins to the coils. So one of the we've got a coil 1, coil 2, and NA is the common, I would imagine. So not sure where that common is connecting to, actually. That doesn't seem to go anywhere. Unless it just doesn't have... Unless they just leave it floating on this. Maybe. Fine. So then the power, V, that goes up the side there. That just goes straight into the IC. That's all it goes to. That's it. And also to the other side of the capacitor. Then our speed sense, that's coming up the side and going to that pin there. And then we've got PWM, which goes up to pin 1 in the top right there. So really, to learn anything about this, we need to look at the circuit diagram for this chip. This chip is basically the entire circuit, and that's it. It's got a couple of resistors and a capacitor. That's it. That's the whole thing. So I'm going to look up the datasheet for that chip, and we'll switch to some talking heads to discuss how that works. Back in a moment, everyone. So here's the datasheet for the APX 9173, and we can see from the title here that this one is a single phase one. So that's immediately something different going on, and it also explains why the third pin from the coils wasn't connected to anything. There's actually only one coil in this thing, and the third one is just soldered to the board, literally just for mechanical stability, just to hold everything in place. So there's actually only two pins. There's just one pin 1 and pin 2, and that's just going through all four coils around the magnet. So that immediately makes this one kind of interesting, because with only a single phase, it has to pulse all of the magnets at the same time when the poles of the rotor are exactly in position. However, because this is a smart chip, it's actually very easy for it to do that. And it means that they only have to wire one coil for the whole motor, which makes the motor cheaper to produce. And we can also see that it's got a huge amount more features on it. We've got a soft start function, which means if the fan is stopped because it's obstructed, or you stick a finger in it or something like that, it will stop and then restart. Again, PWM can soft start it. We've got variable speed curves, current limits, lock protection and restart function. Oh, that's what I just said for the other one. And also a quick start function, so it can spool the fan up at maximum speed in order to get it up to speed, and then let the incoming speed control signal then manage the fan speed, and so on. So as you can see, immediately we actually have logic going on in here. It can actually think for itself. So once again, application is for brushless DC fans and motors. So let's scroll down and find the block diagram. What have we got in here? Yada yada yada. So here's the block diagram, and as you can see, there's a huge amount more stuff going on in here. We still have a voltage in, and we've got two outputs. So that's going to be the two ends of the coil. So this one is driving the coil directly, rather than only driving the cathode of the coils. The coils on this fan were not actually connected to the positive rail on their own. The two ends of the coil go straight to the chip, and so it's just managing the power through them. And you can see we've got a maze of MOSFETs doing that. So it can switch these MOSFETs on in a specific order to then flow power through the coil in whatever direction it wants. And there's a couple of other bits and pieces in here. This has a voltage reference as well, which is one of the resistors we saw. However, right in the middle here, we've got the same Hall effect sensor, amplifier, Schmitt trigger. So it's using the same system as the 3-pin fan to detect the position of the rotor as it spins around the controller. And then it takes that into this logic control circuit, which is just the magical black box. And in there, we've then got all the other things, oscillators, current limits, yada, yada, yada. Now we've also got the PWM signal here coming in to the logic signal as well. So notice the PWM signal doesn't go to the output, it's going to just the control circuitry. And that is going to be relevant in a minute when we look at more outputs. So from here, it's the same deal. We've got the Hall effect sensor. As the poles of the magnet in the rotor come around, the Hall plane is going to output to the op amp, to the Schmitt trigger, and then the logic control circuit looks at that and switches the motor on and off using these MOSFETs that are all built into the chip. Then there's a couple of other bits and pieces on this one as well. We've got a minimum speed set, and that's for programming purposes. And we've also got a this FG output. We can see back up here, and we can see up here that it also has FG, rotation speed detection. So that's not something that we need in the fan, but it just means that this chip is also actually capable of detecting what direction the rotor is moving in. So yeah, that's an interesting thing. So again, this is actually an incredibly basic circuit. However, most of the interesting stuff is all handled just inside the chip. It's just a magic black box that has just got all these cool features built into it, because it's actually a logic chip and actually thinks, rather than the 3-pin fan controller chip, which was what you could refer to as an analog chip. There's no actual thought process in that chip at all. It literally just reacts to a signal going in and a signal going out. It has no ability to change any of that. Whereas this guy actually has some logic in it, so it can look at signals going in and out of it and decide what to do with that information, which makes it incredibly more sophisticated. Okay, right, so I've soldered a wire onto an L1, so we've soldered a wire onto one end of the coil for this motor, so we can look at the power going through it and see what it does. So I'll hold the fan and power it up again, just get that at a comfortable angle, and power on. Alright, let's see if we can find the signal here. Right, is that faster or is that slower? It's slower. There we go. Alright, so we've got just over 70 Hertz at about a 45% duty cycle. So that's not terribly exciting, to be honest. It's just another square wave. But then on the other hand, that's exactly what you'd expect, really. It's just pulsing 12 volts to that coil. So all it's doing is just pulsing the coils at 12 volts and just nudging the fan around every time the magnet is in phase. And what we'll find is if we manually slow that down by touching it there, as you can see, the frequency is getting lower. So the fan is using that Hall effect sensor to detect the rotational speed of the rotor. And when it goes slower, it's slowing down the pulses to the motor in order to make sure that it keeps pulsing the motor only when the magnet in the rotor is lined up with the coils. If I stop that altogether, it goes dead, and after a few seconds the auto restart will kick in. There we go. And as you can see, as it came up to speed, the frequency increased. Now, I didn't notice this at the time of recording, but if you look at these numbers, we can actually put some context to them. We've got a frequency of approximately 70 Hertz, so that's 70 cycles per second. Now, the rotor's magnet is a circular magnet, so it will have 4 poles, 2 north and 2 south. So if we account for that, if we divide 70 by 2, we get 35. And so that accounts for there being 2 north and 2 south, so it's obviously pulsing twice per second. Now times 35 by 60 to convert from seconds to minutes, and we get 2100. So that would be about 2100 RPM. And around about 2000 RPM or so is exactly what we would expect to see from this fan while it's spinning at not quite full speed because we're at 10 volts. So we can actually see from this frequency, we could actually calculate the approximate RPM of the fan. Now, I really wish I'd actually bothered to set up the tacho signal for this, the speed sensor, because then we'd be able to compare those numbers and show the relationship between the RPM reading of the fan and the pulses going to the motor coils. However, we can actually see that in action here. And when I slow down the fan, obviously the frequency decreases because the RPM decreases. And we could probably calculate that and figure out the RPM then as well. So what we'll do, let's try feeding a PWM signal back into it again and see if that has any impact on what this looks like. Because on the 3-pin fan, what we would see is that any fiddling, any fiddling we did with the voltage going into the 3-pin fan, whether we pulsed it or whether we just lowered it, we would directly see that going into the coils, because the chip on that was completely unintelligent and just passing all the information going into it straight through to the coils. Whereas on this one, because it's a smart chip, we should actually see that it should be unaffected by the PWM signal. Or will it? I don't know. Let's find out. So let's turn that off again. How strange. Okay, so the fan is running, but it's completely altered the characteristics of it. You can see we've got a completely different signal now. Right, so I don't really know I'm not sure how to read these numbers, because obviously it's showing a very high frequency there, but I don't know if that frequency is represent. Hang on a sec, let me just zoom into that. Yeah, so now the frequency we're seeing is about 500 hertz. However, as you can see, it's interrupted. So what I want to know now is that in time with the PWM signal? Is the chip passing the PWM signal straight into the motor, and we can actually see the motor being switched off on those intervals? Now I'm going to voice over this section here because at the time when I was recording, I didn't really understand what I was looking at, but now I'm reviewing the footage, I've actually made more sense of it. So as you can see here, what's actually happening is the PWM signal is appearing inside the on cycles of the motor. Now, while I was recording, this was blowing my mind. I was like, what the hell? I don't understand. How is it like that? That makes no sense to me. However, when you actually consider what the motor coils are having to do, it makes perfect sense. Because if we had the PWM signal going straight through to the motor coils and we were pulsing the coils all the time, we would pulse the coils when the rotor is completely out of phase. And it would not work. It would completely disrupt the operation of the motor. But instead what's happening is the control chip is injecting PWM in the on cycles of the motor. So when the coil turns on to push the rotor around, it's actually getting PWM pulse during that on cycle to weaken the pulse that it's giving. And that's why it looks really funky like this. So here we really see the true genius of what the PWM controller chip is actually doing. For a long time, I just assumed that the PWM signal going to a fan was literally just turning the fans, the whole circuit on and off really quickly. But actually it goes to an actual logic circuit that interprets and then that interprets that PWM signal and pulses the motor within its own PWM signal, if that makes sense. I hope I'm making sense in explaining this because, as I say, this revelation, it's when you understand it, it obviously is very obvious. But while I was recording this, it blew my mind. I was like, what? And now I'm looking at it now, I'm just like, that's really clever. So yeah, that's what it's doing. So right now we've got no PWM and it is just showing our normal 70-ish hertz frequency. And then when we apply the PWM again, you can see that we now have the PWM signal inside the on cycles of the motor coil. So the basics are, as we saw with the 3-pin fan, you start off just by feeding in 12 volts and the Hall effect sensor will just simply chop that up. It will send it to one coil, and then when it senses the magnet pole coming round on the rotor, it will alternate to the other pole, and then it pushes the rotor around a bit more. However, on this digital one, the chip is generating a square wave going to the motor, and when we interrupt that with a PWM signal, the chip then injects on-off cycles into its own PWM signal, if that makes sense. So yeah, I hope you guys found that kind of interesting. I think I've more or less reached the limits of what I can show you here. As you can see, I'm kind of on the edge of my knowledge here where I'm just figuring this out. But I hope you guys found that kind of interesting. That was a teardown of a 3-pin and a 4-pin fan. And as always, stick around for the end card because all my support links and also the link to my Discord channel are in there, and they're also in the description down below. Thank you very much. See you next time. Bye.